All right, in the second half of the 1.2 video, we are going to continue learning about how we solve linear systems in matrix and continue to solidify our vocabulary in doing so. And so the first thing on this page, if you kind of think about where we were on the last page, we finished solving, we did the in-class activity, and we finished sort of thinking about row reducing and what solutions to systems look like. And this list right here sort of lays out more specifically what you need to do to solve a linear system. So the first thing you do is you write down the augmented matrix. So you put the system into a matrix, right? Then you use row reduction techniques to get an equivalent augmented matrix in echelon form, right? And so this is telling us to do row echelon form and see if it's consistent. All right, that's what step number 2 says. Put it in echelon form, decide whether or not it's consistent. If it's not consistent, that means there's no solution and there's no reason to go any further. If it is consistent, i.e. you don't get something that says 0 equals not 0, you continue to the next step, which is to continue row reducing to fully reduced echelon form. And so this is kind of a key thing here. If you're going to actually solve a system, I'm going to ask that you use the fully reduced form. It's technically possible usually to solve the system in REF, but it's much easier, and I'm going to be looking for you to solve it in fully reduced form, which is what the last first half of 1.2 is all about. Once you have it fully reduced, you can write down the system of equations that correspond to the matrix, just like we did in the last step, in the last class, I mean. And then, once you have that, you can rewrite each non-zero equation from number 4 so that the basic variable is expressed in terms of any free variable. So you want it to look like basic variables equals free variables. And you might be wondering what basic and free variables are. That's what's defined right below here. So a basic variable and free variables are both defined right here. So a basic variable is any variable that corresponds to a pivot column. So if something has a pivot in it, we say that that's a basic variable. All the other variables that are not in a pivot column are free variables. All right, so we've got an example matrix right here. I'm going to go ahead and box in the pivots. Right, so a box is going to be our pivot entries. We know the pivot starts in the upper left-hand corner right there. And then we go down and right to get the next one, down and right to get the next one. So this one has 3 pivots, right? Now let's also remind ourselves that the columns are the variables, right? So this is like the x1 column, x2 column, x3 column, x4 column, x5 column. This is the equal sign, and then we have the constants on the last column. And so if we want to think about what the pivot columns are, right? The pivot columns are the ones that have pivots in them. So the pivots would be x1, x3, x5. So it's going to be columns 1, 3, and 5. Those are the pivot columns. And so then, therefore, the basic variables are the variables that are associated with those columns. So x1, x3, and x5. All right, so these columns tell us what the basic variables are. And so then the free variables, like it says right above, are all the things that are not basic. So the free variable, as in this case, would be x2, that doesn't have a pivot, and x4 also does not have a pivot. Okay. Wonderful. So it turns out if we're looking at this matrix and we want to go ahead and solve it now that we kind of know what the pivots and the basic variables and the free variables are, we want to double check to see if it's in echelon form. That's the first step, and this one is in echelon form, and it's actually fully reduced, right? Because we've got a pivot in that column. It's the only non-zero there. There's also a pivot, so down right here's the next pivot. It's the number 1, and it's the only non-zero in that column. Down to the right, the next pivot, it's a number 1. It's the only non-zero in this column. So this is in fully reduced form, actually. We don't actually have to do any work to fully reduce this. And so we can go ahead and solve the system, right? So we put it in echelon form. We don't have something that looks like 0 equals not 0. It's fully reduced. And so we're right down to step 4. Well, we write the system of equations corresponding to the matrix. And so I'm going to go down to this step down here and do that. Right? So the final step in solving the system is to write down the set of equations. And so the set of equations are actually going to be written down right here. And so the first row says x1 plus 6x2 plus 3x4 equals 0. The second row says x3 minus 4x4 equals 5. And the third row says x5 equals 7. Okay, so we write down we just did step 4, we wrote down the set of equations. And then step 5 says, write the basic variables in terms of the free variables. Right, so the basic variables are 1, 3, and 5. But notice that the free variables, x2 and x4, show up in those equations. And so sort of the final step to solve these things is to solve for the basic variables in terms of the free variables. So again, the free variables are x2 and x4. And so I'm going to write things that say basic variables, x1, x3, and x5, equals things with just x2's in them, right? So in other words, I'm going to solve this equation for x1 because x2 and x4 are the free variables. So the first equation becomes x1 equals minus 6x2 minus 3x4. Right, the second equation I'm going to solve for this basic variable, x3, in terms of x4. So x3 equals... I'm sorry. Let's go down to one. I skipped x2, right? So I did x1. I got an example for x1, or a solution for x1. x2 is a free variable, and so I mentioned this last time. The way you write free variables, or a nice way to write them, is just to write x2 equals x2. This just says that this is a free variable. It could be anything. Sorry, let's go to the next equation now. We can write the next equation in terms of x3, because that's another basic variable. So x3 equals 4x4 plus 5. x4 is another free variable, so x4 just equals x4. Right? It is also free. And x5 we have just equals the number 7. And so x5 we actually get a constant value for x7. 7, excuse me. And then we can put it all together to write down the general solution, because we have now an expression for x1, x2, x3, x4, and x5, right? It's that expression right there. So the general solution is x1, x2, x3, x4, x5 equals each one of those things. So x1 is minus 6x2 minus 3x4. x2 is a free variable. x3 is 4x4 plus 5. x4 is a free variable. And x5 was 7. And so that's how we get a general solution for that. Another way we can express that solution is by using a parametric description, like it says at the bottom here. So let's read this. The general solution of a system provides a parametric description of the solution set. You can see that the free variables act as parameters. In other words, right, the free variables x2 and x4 were inside the solution of that last problem. And so they're parameters in the solution. Now take a second to think about the last question here. This system, this solution, has infinitely many possible solutions. Why is that? Just take 1 second and think, how is it that we could get infinitely many solutions from that one? Well, hopefully you were thinking about, because you can plug anything into x2 and x4, right? Those are free variables, which means they can be anything. And so whatever you plug into the x2 and x4 becomes a solution. And since you can plug infinitely many things in, there's infinitely many possible solutions. So let's write that down. So the idea is that since x2 and x4 are free variables, that means they can be any number. So let's just show a couple specific solutions. So this is the general solution because it has the free variables in there. If we want a specific solution, we just plug numbers into x2 and x4. So for example, let me get another color here. If we let x2 be 1 and x4 be 2, if we plug those into those variables in that solution, then the solution would be as follows. We get a specific solution, which would be minus 12, 1, 13, 2, and 7. And so these are x1, right? This is like an x1 value, x2, x3, x4, x5. And so the idea is if we plug those values into our original system, it would satisfy the system because it's a specific solution given some of the free variables. Just to kind of drive that point home, we could plug anything into x2 and x4, right? So let's just plug in 0 into both of them to get a nice easy solution. So if we plugged in 0, the solution would be, right, we just plug in 0 to all the x2s and the x4s, and we get 0, 0, 5, 0, 7 is a solution. And so again, we call these specific solutions. So the general solution has the free variables in there. These right here would be what we call specific solutions, because they're actual values for those parameters, for each variable that would actually satisfy those equations. Okay. The next page sort of gets at how do we know when there's infinitely many solutions, and what might we know when there's just one solution, right? And so the short of it is we get infinitely many solutions whenever there's a free variable, right? So we need to have variables in our answer to have infinitely many solutions, i.e. we need to have a free variable. And so thinking about when are we going to end up with columns that don't have pivots in them is sort of what the next page is all about. And so let's look at that. This is sort of talking about existence and uniqueness questions. And so we know that a solution exists if the matrix is consistent, right? But uniqueness, so when is there a unique solution, that gets at whether or not there's free variables. And so let's look at a couple examples, and then we'll sort of make a general statement about when that's going to happen. So here's a system. We could solve this system by putting it into a matrix and reducing, right? So I'm not going to show you that work. Let's just put it in REF. And I'm just going to say that the work is not shown for this. So I'm just skipping right to the reduced form. And the reduced form looks like this. So it's 3 minus 9, 12, minus 9, 6, 15. 0, 2, minus 4, 4, 2, minus 6, 0, 0, 0, 0, 1, 4. Okay, so that's the reduced form. Again, I got that from a calculator, not showing the work there. Let's also keep in mind where the pivots are. So I'll box in the pivots like I have in the past. Right, we know this is a pivot, down right, this is a pivot, down right, this is a pivot. And also key to this is knowing what variables those are associated with. So I'll just remind us this is the x1 column, x2, 3, 4, 5, and then we've got the constant. So first of all, we have a solution, right? So we have reduced form. It's not fully reduced because these pivots are not the number 1, and we don't have zeros above those pivots, but it is reduced so we can see whether there's a solution. And none of the rows say 0 equals not 0, right? And so we have a solution, right? So let me just make that clear. So no row says 0 equals not 0. And so system is consistent. i.e. it has a solution. We see that the pivot columns are 1, 2, and 5, and so that means x3 and x4 are free variables. So x3 and x4 are free variables. In other words, they can be any number. And so we're not going to write the solution down to the system necessarily because there's a lot of variables, and that's not really the point here. I'm just trying to point out that before we even do anything else, just by reducing it to row echelon form, we can see that we have a system. We have a consistent system, so there's a solution. And since we've got some free variables, that means that there's infinitely many solutions, right? So we're going to get a parametric form that has these free variables x3 and x4 in the solution itself, right? And so the takeaway here is if you end up having, oh, I forgot this pen's dying. So if you have a consistent system with a free variable, at least one, all you need is one, but at least one, this implies, and I use this arrow a decent amount, so let me just sort of mention that if you haven't seen that before, that's math shorthand for implies. This implies that there are infinitely many solutions in the system. In other words, you're going to have the free variables in the solution. And more specifically, in this particular example, since x3 and x4 are the free variables and x1, 2, and 5 are not, we actually get x3 and x4 in the expressions for the other ones, right? And we should also kind of notice too here that, notice that x5 gets a value again, right? So this last row right here just tells us that x5 is actually the number 4. And so you can see that if we wrote down the equation for x1, it would have these other variables in it, specifically the free variables. Same thing with x2. And so let me just sort of make that clear. In this particular case, the solution would look like this. So the x1 is going to have free variables in it. x2 is going to have the free variables in it. So it's going to be functions of the free variables. That's what I'm saying here. I'm saying the x1 spot is a function of the free variables. The x2 spot is a function of the free variables. x3 is free. x4 is also free. And then we notice that x5 actually has the value of 4. And so x5 is going to take on the value of 4. Excuse me, not 5. And so this is sort of what the solution is going to look like because we've got free variables. And I would also just ask you to think real quick, like what kind of system is automatically going to have free variables, right? So in order to have free variables, we need to have columns without pivots. This system right here has the most pivots it could possibly have because we could pivot in the upper left, down right, pivot here, down right. So you can only have as many pivots as there are rows, right? And so if you have more columns than there are rows, you're going to end up with columns without pivots in it. And so you can have, there's lots of different ways to get free variables, but what I'm trying to point out is if you have more columns than rows, you're automatically going to get free variables, like in this case. If you have a consistent system, of course. So free variable, infinitely many solutions. We are guaranteed to have a free variable if we have more columns and rows. Get this fly out of here. A different thing happens in the second system. So let me again write down just the completely reduced form of this. So again, I'm just going to write down, not the completely reduced, the row echelon form of this. Again, I just did this with the calculator, which we'll learn how to do sometime in this course. And when I reduce this system, I got this. And so notice in this one, since there's 3 equations and only 2 variables, we have more rows than we do columns. And so there could be at most only 2 pivots in this one, right? Because we have a pivot right here. You go down and right, pivot right there. You couldn't have another pivot with a consistent system because that would imply the pivot would be over here, and then we get 0 equals not 0, right? And so in this particular system, x1, x2, constant, we have two pivots and no free variables, right? Because each column has a pivot in it, each variable column. And so since we don't have any free variables, we're going to end up with a unique solution on this one. And so before we even do anything, I know it's going to be a unique solution, but let's go ahead and write it down just for practice, right? So we've got it in reduced form. It'd be better if we fully reduced it, but this is easy enough to solve because it's a nice, easy system, right? So this row right here just tells us one of the answers. This says x2 is 3, and so that's one of the solutions. The first row says 3x1 plus 4x2 equals minus 3, and so you can take this solution we just found and plug it into the x2 to find out what x1 is. Right? So what we really have is 3x1 plus 4 times 3 equals minus 3. Now you can get x1 by itself pretty easily and find out that x1 is negative 5. Right, so we have a unique solution here, right? Our solution in this particular case is x1, x2 equals minus 5, comma 3. Or sometimes we could write it as a vector like this. Right, we'll learn more about that as the course goes on. But the key thing that we're trying to just point out in this particular example is we had no free variables, and that led to a unique solution, right? So free variables means infinitely many. If we have no free variables, that means we get unique. And so we had no free variables. We had a consistent system. So no free variables and a consistent system. That implies that the solution is going to be unique. In other words, we get all numbers, right? There's no variables in our answer because it's a one unique specific solution. In this particular case, our unique solution was minus 5, comma 3. Okay. So this page, like it says at the top, is about existence and uniqueness. So we know we have a solution exists if we have a consistence matrix, which we've learned about in section 1.1, and we know it's unique if there are not free variables. And we've also sort of talked about how we know if we're automatically going to get a free variable, right? More columns and rows. If you have more rows than columns, assuming you get a consistent system, we won't have a free variable. If we have a square matrix, then either one of those things can happen, and we will see different examples of each one of those things happening over the course of the course. Okay. The final page is one last in-class activity. Again, usually when I teach this in person, we break up into groups and divvy up some of these questions. Each group does at least one of them, although groups who go through them quickly oftentimes are able to do all of them, etc. And so this is your chance to give some things a try. In the first example, in the first problem here, you're supposed to look at each one of these matrices, think about whether they're fully reduced or not, and if they're not fully reduced, describe in words how you would reduce it. So I'm not actually asking you to fully reduce it, just sort of think through what the steps might be in each one of those cases to fully reduce that if they're not already. In the second two, we're going to put these into a system and fully solve them. So row reducing them, seeing if there's a solution, and then writing down that solution using the steps on the previous couple pages. And then the third question is just kind of like a quick thinker. This is actually a really easy question that doesn't require much work. What do fully reduced and just partially reduced matrices look like if they're just 2 by 2? Right, so as a quick reminder what that notation means, 2 by 2 means the number of rows and columns. So 2 rows, 2 columns. In other words, square matrices that are really small. So a 2 by 2 matrix in general looks like this. That's a 2 by 2 matrix. So what do 2 by 2 matrices look like in reduced forms? I would strongly encourage you to at least think about these ones up here. Try to reduce a system as far as you can by hand. If you're feeling confident about this, try them all. If you're a little bit shaky, maybe get as far as you can and then watch me do it in the video. Again, this is really helpful for you to sort of dig your teeth in, try, If you get it, great. But if you don't get it, then you can see me correct it on film, and then that's going to be very helpful sometimes. You're also going to need more space than this, right? So these two problems in particular will probably require their own page. All right, so hopefully you did take a second to pause the video and at least think about that a little bit. I'm going to go through these one at a time. I do have enough space to kind of cram in the answers to these. And so let's look at these three matrices and think about, are they in row echelon form? Are they fully reduced? If it's neither, how would you get them into those two forms? So let me do the pivot. So pivot on this one, down right, pivot here, down right, pivot here. Okay, so the pivots are all set up. This is not the number one, so it can't be fully reduced. And the pivots have other numbers in the columns, right? And so this first matrix is just in REF, just echelon form, because, again, this is not the number one, and we've got other things in those two entries. They would be zeros if it was fully reduced. So it's just row echelon form. If we were going to get it into fully reduced form, we'd want to make that a number 1. And so we would divide row 2 by 2 to make that a 1. And then we would use that entry to cancel out the one above it. And so that's the 2, 2, comma entry, right? The second row, second column. So then we would use the 2, comma 2 entry, the one right in the middle, to eliminate the one above it. And the one above it is the first row, second column. So that's the 1, comma 2 entry. So just to be clear, I know we're still kind of early in the course. That's in the form row, comma column. And so that would take care of that middle column. And then we would use this last entry to eliminate the 2. And so we're just kind of thinking through. We're not actually doing it. We're just thinking through what the steps would look like to fully reduce it. So the final thing would be use the 3, 3 entry to eliminate the one above it, to eliminate the 1, 3 entry. So if you weren't really clear about what you're supposed to be doing on that first one, hopefully it's clear now, and maybe you can think through the second too. So let's look at the pivots in the second one. So pivot in the upper left. You do go down right to get the second pivot if we wanted to include that one, but you can't go down right to get this one, right? So those two are messing up the pivot structure. And so right off the bat, this is neither REF or RREF because the pivots are not in the right places. But it's a fairly easy fix, right? If you just switch these two rows, if you switch rows 2 and 3, it will have the correct structure. And then you would do the same thing we did in the previous one, which is use this one to eliminate that one, use this one to eliminate that one. Right? So let me just write down those steps. So the first thing we would do is switch row 2 and row 3 to get the pivots in the right spot. And that would make it REF. And then you would do literally these same steps as the previous one. Then same steps as number 1. In the last one, let's box in the pivots one more time here. We got pivot, down right, pivot, and then the bottom has a row of zeros, and so that's good. And so the pivots are all set up. We've got the zeros at the bottom. The pivots are the number 1, and those pivots are the only non-zeros in those columns. And so this is fully reduced. This is RREF, right? It satisfies all those conditions. And so there's nothing left to do to get it in full REF. So let's just talk about free variables just to kind of clarify that a little bit more. So this would be a free variable, right? This would be a free variable. And so these would be our free variables. This one is probably the equal sign. So this is the constant over there. So that's not a free variables. And so since we have free variables, we would have a not unique solution. So we'll have not a unique solution because we've got free variables, i.e. we'll have infinitely many. All right. Hopefully those made some sense to you. For these two here, I actually have the solutions written up, so to save us a little bit of time, so I'm going to put those up and kind of walk through them. So the first case here, I'm going to put this into an augmented matrix, and let's see what that looks like. So here's the augmented matrix from number 2. You can see that I've got a pivot in the upper left-hand corner already, which is what we want. And so then we want to use that pivot to clear everything out in the column, right? So I would use that to clear out that -1, and that's a real easy step. You just add that one to that one to clear it out, right? So the first thing we want to do is take row 3, add to it row 1 to clear out that first column, and then the first column ends up being all set, right? But you need to do the same thing with all these. You add all these together to get this second matrix there. And then when we're thinking about the pivot, you go down right. This would be our next pivot. And so we would use that to clear out the one below it, the 4. So we multiply this one by 4, this entire row by 4, and add it to the third row, right? So row 3 plus 4 row 2 is going to end up using that to cancel that. And when we get it into this form, it's fully reduced, right? Pivot, down right, pivot. We got entire row of zeros at the bottom. The pivots are the only non-zeros in the column, and so this is fully reduced. And when we see it in this form, we see that we've got 2 basic variables, x1 and x3, and then the free variables are going to be x2 and x4. And so when we write the actual solution down, we write the basic variables in terms of the free variables, right? And so here I am just writing the equations down. Right, so I've wrote down all the equations from this, oops, I forgot to put it up. I've written down all the equations from the matrix, including the free variables, right? x2 is free, x4 is free. And then you solve for the basic variables in terms of the free variables, right? So the general solution, we do the basic variables x1 and x3 in terms of the free variables x2 and x4, right? So I just solved these 2 equations for x1 and x3, and here's the full-on solution, right? We have an expression for x1, 2, 3, and 4. x2 and x4 are free variables, so they're just equaled whatever they want. And then they also show up in the right-hand side of the other solutions. Okay, so we got free variables on that one, which led us to infinitely many solutions with free variables in the answer there, right? And so then the second one actually ends up not having free variables. So let me show that one. So here is the second system written in augmented form. Right, so I've taken the second system written in a matrix. There's the first pivot. I want to use that pivot to get rid of the one below it, so I'm going to multiply this one by 2 and subtract it from row 2, excuse me, which is exactly what this is, right? Taking row 2, subtracting 2 times row 1, and we get this. And this is now REF. And it's consistent, right? So I should write my equal sign in here. We've got our equal sign. We don't have a row that says 0 equals not 0, and so it's consistent. And so then we can use this 1 to cancel out that 4. So I'm going to do row 1 plus 4 row 2 so that this becomes a 4, and then it cancels that one out, right? And when you do that, you get this nice matrix here, which is fully reduced. I guess technically there's a -1 here actually, so like I wrote down, if you want to get it fully reduced, you multiply this one by -1 because we want a 1 there, right? So this is technically the fully reduced form with those switched around. But the point is we have no free variables, right? I think I'd like to just make that clear. We have no free variables in this, and so x1 and x2 are both basic. And so when we write down the answer, it just says, right, x1 equals -9, minus x2 equals -4, and so we get a unique solution, right? We get a solution of -9, 4, because there's no free variables. All right. In the last example, I think I can probably write it right down here. If we want to think about row echelon forms of a 2 by 2 matrix, we need to have a pivot, and let's assume that Let me think about that for a second. Yeah, so if we want to have row echelon form of this particular form of a matrix, we want to have a pivot in the upper left, right? And then there'd be a 0 below it. So row echelon form of any 2 by 2 is going to look like this. Right? And so we need to have a 0 in that spot. Right? The C equals 0 in this one, right? And D could be 0 or not. And it would still be an REF. If we want it to be fully reduced, our REF it would look like this, right? And more specifically, if we have a pivot in the upper left-hand corner, it needs to be the number 1. And then D could either equal the number 1 if it's a pivot, or it could be 0 as well, and it would still be fully reduced, right? So if it equals the number 1, this is going to result in a unique solution, because there's no free variables. And if D ends up being 0, then this is going to be a free variable, and we'll get a not unique solution. So x2 would be free, and so we get infinitely many solutions. So just kind of thinking through, like, what does a 2 by 2 reduced matrix look like in general? If you kind of understand what I'm saying there, you should have a good understanding, I think, of what row echelon form is. All right, that's the last part of 1.2. In 1.2 we start, or excuse me, 1.3 we start breaking things down into vectors and moving forward with that.